Okay, so our second lecture today is by Dmitry Kaledin, and we thank his presence here, and he's going to talk about deformation quantization in algebraic geometry.
Thank you, and thank you very much for inviting me here. It's a great pleasure to be here and really impressed. So the topic is deformation quantization in algebraic geometry. And I'm very lucky that today we have two talks, and Enrique actually explained quite a lot about just general deformation quantization setup. And as he mentioned, what I'm going to talk about is some restricted part of deformation quantization. Actually, some people may consider it even obsolete. So it's Fedosov quantization, which only applies to symplectic manifolds and doesn't really use this conceived formality and all the other advanced things. So it's a bit aged. But on the other hand, the results which you can obtain in this case are stronger. So I think it makes sense to treat it separately. And I'm going to concentrate on algebraic geometry or holomorphic geometry, but not C-infinity geometry. And in this situation, things are a little bit different, but not so much different. So when I first started working on this, I don't know, 15 years ago, it looked like it's a very stupid thing to consider. That obviously the two worlds are quite far apart. One is symplectic manifold, C-infinity manifold in physics, and the other world is algebraic geometry. But turns out, actually, with some modifications, many things can be worked in a pretty similar fashion, and we get some results which are actually useful for algebraic geometry, at least. But so let me start with defining exactly what I mean by quantization. So I start with some x, which is an algebraic variety over some field k. So if you don't like arbitrary fields, you can say that this is just complex numbers. And the whole story also has a counterpart where x is just a complex variety, so it's a holomorphic variety. So I will stick to this case, at least in writing, but most of the things can have two parallel versions. So when we have algebraic variety, we have functions on x, but sometimes we have not enough global functions. So it makes sense to consider the sheaf of functions. So we have structure sheaf. This means that for any open subset U, in X you have kind of functions on U, and then we have two subsets which one inside the other have restriction map, and there is some kind of gluing axiom. And in algebraic geometry, we always have to work with sheaves because unlike the C-infinity setting where you have enough global functions, here quite often global functions are just constant, for example, so there's not enough of them. So my notion of quantization then, it's also in the sheaf form, so my definition. Quantization of x is again a sheaf of, so I'll first give you a definition and explain the meaning of the words. Flat K of H algebras. By algebra, I always mean something associative and unital, but maybe not commutative. Complete in H-ASIC topology. And it has to be equipped in isomorphism, OH modulo H, isomorphic to OX. So what does it mean? First of all, a sheaf, this means that for any open subset here, we have some genuine algebra, H of U, so associative algebra, well, over our field K, but also we want one formal parameter H, associative algebra over K of H. And formal parameter means that this is the ring of all arbitrary power series. I don't care about convergence, just all power series. Flat just means that there is no H torsion. And complete means that if I have some expression like f plus hf1 plus h square f2 plus so on, every expression like this converges. So there is some kind of projective limit topology on OH, and with respect to this topology, everything converges. And I have this isomorphism. So as far as relation to physics is concerned, this is even further apart, because as Enrique explained, actually what people want in physics, they want two things. They want the algebra of observables, and then some representation of this algebra, which is called the space of states, on which the algebra acts. Here we completely forget about states. So this you can also consider, but this is a second step from this point of view. They only think about the first step, and they only think of constructing such an algebra. And moreover, here we don't actually have a reasonable global algebra, we only have it locally. So for every open subset, you have something like that. But nevertheless, everything is well defined, even in the context of algebraic geometry. So perhaps, so there is a kind of, and defining this in algebraic setting is actually quite strong because, I mean, what does it mean to consider variety algebraically? This means that there is a notion of a polynomial function there, and we only consider polynomial functions. We don't allow arbitrary smooth functions, only allow polynomials. And you would expect there's, so as Enrique explained, in the infinity setting, this thing also has to be a formal power series always, because when you write down star product or something, there is typically an expression which is infinite in the powers of H. So here you would think that if you only have polynomials, you can maybe get rid of it and really have something where you can, for example, later set H to be equal, say, to 1. But turns out that in this generality, it's impossible. Let me explain why. So kind of observation. H has to be a formal parameter. And this kind of the payback you have to pay for working with arbitrary sheaves. So let me explain an example. So we can take as our x just a fine space of dimension 2n. Then functions on x, I only consider polynomial functions. So functions are just polynomials. So algebraic notation for functions is like this, global sections of the sheaf of functions. And these are just polynomials in some variables, P and Q. And then there is a kind of preferred quantization of this algebra, preferred one-parameter deformation, which is, I will denote it by D. This is actually called the Weyl algebra. And so this is also generated by P and Q plus one additional formal parameter H. And the relations are as follows. So here the relations are just that everything commutes. So this is just a commutative algebra. Here we modify this. So the relations are, so P's, so these guys commute between themselves, so do Q's. But when you try to commute something from here and something from here, so Pi Qj minus Qj pi is h times delta symbol. So if I and j are different, they commute, but if I and j are the same, then there is a non-trivial commutator here. So these are all the relations. You can show, I mean, you have to prove it, but it's not difficult, that this thing is actually a one-parameter deformation in this sense. So in fact, that d modulo h is isomorphic to this algebra. Let me call it A. But if you look at this definition here, you can just put h in, just treat it as a not as a formal variable, just a general variable. But this only gives the deformation of the algebra of global sections of OX. And in order to develop a theory which works for varieties which are more difficult than just affine, we need to have this sheaf thing. So we need to be able to localize. So how do we do this? So we need to take some open subset and also construct an algebra like this. And so what's a typical open subset in algebraic variety? You take some function. You take the subset of its zeros. The second dimension one subvariety, which is a divisor here, and you take U, which is the complement to df. Then functions on U are obtained from functions on X just by formally inverting F. It's called localization. Typical algebraic procedure, which you can always do with a commutative ring. You just, so elements here are something like formal combinations, A times F to the power n, and you can easily write down the relations for them. And then the problem is that this procedure works very well for commutative rings, but it doesn't work so well for non-commutative rings, because you might have F to the power minus 1 on the left or on the right, and you need to wait to transport one to the other. And for a general non-commutative ring, it's not possible. And in order to be able to do this, in the algebra D, we need this to be a formal thing. So then global sections of my quantization will be obtained by localizing D, where F tilde is some lifting of F to an element in D. So it's something here which gives F under this isomorphism. But then in order for this to be defined, you need to know that for every element A and D, there is always a relation like this, maybe some A prime times F to the power minus 1, where A prime is something expressed in terms of A. But if you write down what this is, then this will be A plus some A1H, A2H square, and so on. And this goes on to infinity. So in order to do this, you have to really you only can do it by considering formal power series. So for physics, this is completely useless, because physics happens when real quantum physics happens when you set h equal to 1. This is at best something which is called, I don't know, like quasi-classical limit or whatever, really near the classical limit. So that's an important thing to keep in mind. But fortunately, this is all you have to keep in mind, because once you define quantizations like that, theory becomes consistent. So for example, there is a lemma which says that if you have some variety which is affine, which means that it's a closed variety of affine space, it's completely defined by the algebra of functions on it. So A is the algebra of functions. Then quantizations of X are in natural one-to-one correspondence with quantizations of A, where by this I understand algebras AH, again over a formal power series, equipped in isomorphism. All right. So here the notion of quantization becomes completely unambiguous. You can either quantize this algebra or the sheaf, it's all the same. And moreover, so when you work in the C-infinity setting, if you want to define things carefully, then as Enrique mentioned, basically what you do, you define a star product. So you consider something like A of H just as a vector space, but then you put some star product here, which defines a new product in this algebra, which is the same modulo H, but then there is additional terms. And in the C-infinity setting, you have to take care, you only consider those star products whose coefficients are given by some kind of differential operators. Turns out that in the algebraic setting, you don't need this. So it's a lemma that whenever you have something, it's equivalent to something defined by differential operators. So differential condition is automatic. Uh-huh.
So you can have a set of points.
Uh-huh. You mean X? Yeah, yes, yes.
How is this kind of, what the meaning of this quantization in that case? Is the simplest case that you can imagine a set of points?
Well, they're all trivial, because you see, when you have points, you don't really have functions which are not constant. So all the functions are just kind of functions which have some value at each point, but there is no so X is equal just to S, right? First of all, if I want this to be an algebraic variety, then this better be finite. And so I didn't quite specify what I mean by an algebraic variety, but it's better to assume the usual things. So it's, let's say, quasi-projective. So it's something which sits as an open subset and a closed subset in some projective space, which means we're basically talking about finite sets of points. Then O of X is just functions on S, arbitrary. But then this has topology, which is just discrete topology. And so every point is an open subset. And defining a quantization of X is equivalent to defining a quantization of every point separately. But for a point, by definition, the quantization is trivial, because you have K, which is a module over K. And you need some kind of module over an algebra over KH, which is equivalent to K, so A over KH, such that A mod H is K. Then such an algebra itself just must be generated by 1, so it must be K of H. So in this case, nothing happens. Just not an interesting case from this point of view. And this is because the topology is discrete, so it all reduces out the points. But if the ring is such that its spectrum is more complicated, then like higher dimension, for example, then you can still do this, and then differential condition is automatic. So all non-trivial star products would be given by some kind of differential expression, where differential operators are in the sense of algebraic geometry, but this is also well defined. So vector field is just derivation of the algebra. So endomorphism which satisfy Leibniz rule, and so on. So you get this notion. Yes. I mean, just for experts, so how do you prove something like this? Deformations are controlled by something called Hochschild cohomology, which I don't want to explain, but like this. You can define Hochschild cohomology for algebras, you can define Hochschild cohomology for things with a sheaf of rings, and the computation says that they're the same. This is absolutely because we're in an algebraic situation, otherwise it's probably not true. I'm not sure about the holomorphic situation, so if you have something Stein, maybe it's still true. But definitely not in the C-infinity setting, because there is much, I mean, the ring of C-infinity functions is absolutely huge. So from the point of view of algebra, it's absolutely out of all control. Right. So fine, so we have things which are well defined. We have an example. And so one additional caution, so when I'm speaking about affine varieties, I can speak about star products. So I have this vector space, and I need to find a modified product there. But if the variety is not affine, then this OH need not be isomorphic to O of X of H, even as a sheaf of vector spaces. As sheaves of vector spaces. So we cannot just say that we have something where I define a new product. We really have a genuine deformation which can be non-trivial even on the purely linear algebraic level. And this is why I define quantization the way I do. Some kind of flat families. All right. Now, so what are the results that one can hope to get in this business? Well, first of all, we have a quantization OH. Then it gives a Poisson bracket. Again, on the sheaf of functions on X, which means that locally we have a genuine Poisson bracket on sections. And this exactly by the same formula which Enrico already had. So F bracket G, you do the following. So you have local sections of OX. You lift them to local sections of OH arbitrarily. You can do this locally. And then you notice that they commute modulo H. So these are liftings. The commutator is divisible by H. Since my thing is flat, so there is no H torsion, you can divide uniquely. And then we don't know what happens at the level of H squared, but modulo H, this is well defined. So this gives you a Poisson bracket. And so you can consider two problems. Problem one, sort of classify quantizations. And problem two is the following. Now you can forget about quantizations, and you can consider simply deformations of the algebraic variety X, but together with a Poisson bracket. So classify Poisson deformations. Just a formal definition. So definition, a Poisson deformation of X is a algebraic variety X tilde over, now not K, but K of H, equipped to the Poisson bracket. Again, the Poisson bracket is on local sections, on the structure sheaf. And such that modulo H, it gives our original variety X. So plus we have an isomorphism, so X tilde restricted to K is identified with X. So there are two problems that you can consider in this situation. And kind of the rough slogan of Kontsevich formality, which again Enrico already mentioned, is that both problems have the same answer. Problems have the same answer. You shouldn't really memorize this as any sort of a precise statement, because in order to make a theorem out of it, it has to be modified, but I don't want to go into it. But roughly speaking, there is a natural space which parameterizes quantization. There is a natural space which parameterizes Poisson deformations, and you can establish a natural identification between them. there is not a one identification, depends on some a priori choices, and there are some minor points when X has homology, but roughly it's like this. So as I said, I'm going only to talk about symplectic manifolds, and in this case, there is a very clean and nice precise statement which I'm going to explain now. So my goal is not to give you any proofs, but at least to give you a statement, and then roughly speaking, explain the main ideas which go into the proof. Right, so our goal is symplectic case. This means, first of all, that X is smooth. Note that up to now, I did not assume that X is even smooth, because for definitions, you don't need this. And it's an interesting thing to consider things which are not smooth. Of course, for formality already, you need to assume that the thing is smooth. And I need to assume this. And moreover, in the smooth situation, as Nick explained, every Poisson structure is given by a bivector. So the bracket is always of the form df times dg, coupled with some, let me denote by theta, which is a section of bivector fields on X. So I want this theta to be non-degenerate. And in this case, the situation simplifies quite a bit. So why this is simpler? This simplifies thing. Well, there's a formal reason and there is a more kind of geometric reason. So a formal reason is like this. If you consider, for example, this problem, the problem of Poisson deformations, then you see that at least in the first order in H, you can show that this is classified by the so-called Poisson cohomology of X, which is the following. You take polyvector fields, and then, as Enrique mentioned, there is a certain bracket here which makes it into a DG Lie algebra. Well, just great Lie algebra. And the condition of the structure of being Poisson, the Jacobi identity, turns out to be equivalent to saying that theta commutator with theta is equal to 0. This is not automatic because theta turns out to be something of degree 1, and this is super Lie algebra. So it's not automatic that something commutes with itself gives 0, but it's a condition. But once you have this, you can put a differential here by just commuting with theta. This gives you a certain complex of sheaves on X, which is called Poisson cohomology complex. And it's this thing which computes Poisson deformations. And now the lucky point is that in the symplectic situation, you can actually use this non-degenerate theta to identify the tangent at cotangent bundle, because it induces an isomorphism. And then this complex just becomes the de Rham complex of X. Complex of X. So in this case, the space which contains deformations actually has topological nature. And formally, this is what makes the deformation theory much more rigid. In particular, as we will see in a moment, under very mild assumptions, there are no abstractions to deformation, so everything is quite nice. But this is just a formal observation. And the thing which is heavily used in the proof is Darboux theorem. Darboux theorem. So when you have an arbitrary Poisson structure, then even in the neighborhood of the point, it can be very complicated. There is a non-degenerate term. If it's degenerate, then there is a local model of, it can be like a Poisson structure on the cotangent space to Lie algebra. But there can be some higher order terms. So there are lots of interesting and non-trivial structures there. Whereas if you know that the thing is symplectic, then locally it has to be standard. So there's a Darboux theorem. Of course, Darboux theorem is in the C infinity setting, and it's local in the C infinity topology. So in algebraic geometry, we have to go to a formal neighborhood of a point. So in a formal neighborhood of a point. But it turns out that this is good enough. And maybe up to now it was okay, but here we definitely have to assume that the characteristic of the base field is 0. So you probably don't care about positive characteristic, but believe me, there is a very interesting story in positive characteristic too. But that story is second level. So in positive characteristic, there could be local invariants of symplectic structures and so on. Things become more interesting. But for this, we need to assume this. And actually, we have even more. So we have this Darboux theorem, which says that all symplectic structures are the same. But in fact, you can show that every quantization of this standard symplectic structure is also isomorphic to the Weyl algebra. So let me now change notation slightly. Let me just to simplify notation. So now I will denote by A not the algebra of polynomials, but the algebra of formal power series in the same variables. And then Darboux theorem says that if you take some point in symplectic variety, then the algebra of formal functions near it is isomorphic to this guy as a Poisson algebra. But moreover, they have this Weyl algebra, which is given, again, I add formal power series. And H with the same relations as I had before, the Heisenberg relations. And then you can show that every quantization of A with this prescribed Poisson structure is isomorphic to D. So locally, we know precisely what's going on. There is no ambiguity. And the problem becomes the problem of globalization of this local information, how this works together when it depends on the point of invariance. So these are the main two reasons why the problem is simpler. Okay. Now let me give you the statements of results for these two problems. And then I think we make a break, and then I can explain kind of the basic ideas of the proof. So let me keep this for a while. So results. So theorem 1 would concern problem 2, Poisson deformations. For both results, I need to impose some assumptions on X. So we have X, and this is symplectic variety, but symplectic variety in the algebraic sense. So I have some omega, which is an algebraic symplectic form, or holomorphic. Holomorphic. So there are two versions of the story. Symplectic form. I mean, like every projective complex variety or every Keller complex variety is naturally a symplectic variety in the infinity sense, but this is not what I want to consider. I want to consider a much more restricted class of examples. But we do have some examples. So for example, we can consider what is called as K3 surfaces. These are certain algebraic surfaces, so it's real dimension 4, complex dimension 2, which have natural symplectic form, non-degenerate. And turns out that, I mean, this is a particular class of surfaces, but they have very rich structure theory, and they pop up in various parts of mathematics. I think they for example, happened to be related to the monster in this talk which we have here in the seminar. And they also relate to physics and all sorts of things. And one thing we can say about them definitely is that they are symplectic. And then, so these are compact complex manifolds. So for example, projective algebraic manifolds. And then there are examples which are non-compact, but nevertheless quite interesting. So it can happen that you have some X, which is smooth and symplectic, which admits, which actually is a resolution of some singular fine algebraic variety. So this is a fine singular. It's a smooth symplectic, and this map is generically one-to-one, birational map. For example, if you have a quotient singularity C2 modular the involution, which sends x to minus x, this is the rational double point, the kind of simplest of the Kleinian singularities, then they have a very nice resolution, which is just the cotangent space of P1. So this thing is affine, but singular. This thing is smooth, but of course it's not affine anymore, but not projective either. So it's in between. It's quasi-projective. So x goes to y naturally, and outside of 0 here, the map is 1-to-1, and this whole P1 goes to 0. And then you can show that if you take, say, T star of Pn for any n, then again there is some y, and there are all sorts of examples of situations like this. So this cotangent bundle is a symplectic variety for the same reason cotangent bundles are always symplectic. So this works exactly the same as in the C-infinity setting, and then you can show that this of this form. So guys like that are called symplectic resolutions. And they seem to have become quite popular lately. For example, Okounkov, he invented the slogan. He says that symplectic resolutions are Lie algebras for the 21st century or something like that. So anyway, there is a bunch of examples which people actually do need in real life. And to them, this theory actually applies and gives results. So they are simpler. So these things are much simpler because they are quite often you can even write them down by equations, and as varieties they're also simpler. So typically those guys are related to a group. You have some reductive group, and you have something like partial flag variety and cotangent bundle of that. Or you have Springer resolution of some kind of nilpotent orbit. I mean, this is the source of origin for these guys. For example, if you look at the cohomology, then you can prove that this cohomology is what is called hot state. So it's actually made out by genuine algebraic cycles. All cohomology generated by algebraic cycles. And you can usually split those guys into pieces with just affine spaces. Whereas these K3 surfaces, they are heavily transcendental. So you cannot really say much about them explicitly. And there is, of course, you can see it in the results. So in the end, when you do quantization for these guys, sometimes you can actually put h to be equal to 1. So you can make it, from a formal parameter, you can make it an actual parameter. Whereas for K3 surfaces, as far as I know, it's not possible. So it's only stays formal. But the theory covers both cases, and I think it's important to have it for the both cases. Now, I need to impose some assumption on x, which is fortunately satisfied in both examples. So assumption. So when you have an algebraic variety x, you have its de Rham cohomology. Well, in the holomorphic setting, this is the same as just cohomology of coefficients in C, but it's also defined algebraically and gives the same answer. And this goes to the cohomology of x of coefficients in the structure sheaf. So I need to assume that this is surjective, well, at least in degrees 1, 2, and 3. But in practice, in both these examples, this is true in all degrees higher than 0. In fact, in all degrees, because, no, in degrees higher than 0, because here you can show that this part simply vanishes. So for symplectic resolutions, it's not difficult to prove that They are rational in the sense that there is no cohomology of the structure sheaf. For K3 surfaces, this thing is not 0, but this map is surjective by Hodge theory, this is given by Hodge theory. So this assumption is satisfied in both examples. Satisfied in examples. And if you wonder what is a bad situation, then a bad situation is something like you take C2 with a standard symplectic form and you remove 0. You just do something like this. Then this has lots of coherent cohomology in degree 1, whereas topologically it's not so big. So the bad situations are really something which you probably don't want to consider anyway. Okay. So let me introduce a bit of notation. So there is this map which is surjective. Let me denote so I need to consider it in degree 2. And let me denote the kernel by H to F of X. This is just the kernel of map from H2 DRAM to H2 XOX. So there's a short exact sequence. And let me choose a splitting. So this is injective, just by definition, it's a kernel. Let me choose some projective, just notation. So this, just by definition, is the kernel of this map. And let me choose some kind of splitting, say eta. I mean, this is a fine dimensional vector space, this is a fine dimensional subspace, I can choose a projection back. So then theorem 1. There exists a smooth subvariety S in. So we take H2 DRAM of X, and as I said, it's a fine dimensional vector space. So let us consider this as just an algebraic variety, just a fine variety. And let us take the formal neighborhood. So when we have a fine variety, our symplectic form, omega, it's closed, so it defines a class in DRAM cohomology. So we have a distinguished element in H2 DRAM. So let me consider this is the formal neighborhood of this point here. So there is a smooth subvariety and a symplectic, or Poisson if you want, deformation of X over S. So up to now in my definition, deformations were just one parameter deformation. I always thought that they are sitting over the formal disk. But now this is a multi-parameter deformation, so it's actually deformation over this S. So there exists something like that, which is universal for symplectic deformation. Universal. So this means that whenever you have some deformations of X together with the symplectic form over some infinitesimal even formal base, then there is a unique map from this base to S such that deformation is isomorphic to the pullback. So it's absolutely the usual sense of universality. And moreover, so to estimate the size of this guy, so if you consider the map eta, then this is an isomorphism between S and the completion of this H to F. So roughly speaking, this is the same size as this kernel here. It's the same dimension, smooth variety of the same dimension. And I could just say that there is a formal deformation of this, but actually it's slightly stronger. So there is a natural parametrization of deformations by DRAM cohomology classes. Not all of them appear, but there is some kind of maybe curved subvariety which sits here of the classes which are good. And this curved subvariety is somehow projects canonically here. So this is a statement about symplectic deformations. So it's so in this generality, it's a theorem of me and Misha Verbitsky. From I forget when, but something like 2002 maybe. But much before, it has been known that for compact, in the compact case, the deformation theory of compact symplectic varieties has no abstractions, and this is due to Bogomolov back in something like 74, I suppose, for the compact case. So in a sense, the general situation is similar. So in the general Poisson situation, you can also find some kind of universal deformation. But unfortunately, there could be abstractions. There could be higher abstractions. So this base of the deformation would be some kind of higher derived stack or whatever it is. I mean, some kind of complicated gadget. Here, the situation is extremely nice. We just have an algebraic variety, which is moreover just smooth. So this is the statement about deformations. And now let me give you a statement about a good example. It's all these are examples of symplectic resolutions. Yeah, so the theory applies. In fact, these were one of the objects we wanted to apply it to begin with. So it's yes. So theorem for quantizations now. So in particular for Hilbert scheme, for example, there is this deformation of something called Calogero-Moser variety. It's a one-parameter deformation. That's the universal guy. And for cotangent bundle to Pn, there's a twisted cotangent bundle. So that's the deformation. Yeah, I mean, symplectic fractional algebra, no. I mean, these are just deformations in the usual algebraic geometric sense. But, yeah. So if this y is a quotient singularity, then indeed there's some deformation of the stack or the algebra of smash product called symplectic fractional algebra, which gives you some Poisson deformation of y. So that one is not universal. It's stupid. So it's actually smooth of the same dimension, but it's a finite ramified cover of the universal deformation, and it's something like a quotient of a vector space by an action of a Weyl group. So that's the picture. But really, yeah. So that's the universal Poisson deformation of y. And for x, that is the one. So if you just consider deformations of x, then for any resolution x, this is the deformation you get. No. I mean, first of all, a hypercalc structure is a much finer invariant than just homomorphic symplectic structure. So for compact case, they are the same, but this is by the Calabi-Yau theorem, which is a strong thing. So this is a purely algebraic. This is actually a very easy theorem. I mean, it's not difficult at all. This is purely algebraic. One thing where hypercalc structures appear is that when you have a hypercalc structure, you have something called a twistor space, which is certainly one parameter deformation of your x to give the symplectic form. So it appears a certain ray here, and so basically go into the direction of one Drumka multi-class. And this is the class of the Keller form. So that appears as part of this thing. But in general, you don't need hypercalc structures for this. No. Okay, so quantizations. Theorem 2. Now we have this deformation, so let's use it. So let me denote by delta just the formal disk in the variable h. So it's just a formal neighborhood of 0 in an affine space, and I denote the coordinate on this affine space by h. Then there exists. So let me consider now h the RAM times this d. So I add one more dimension to the space. So this projects to d, times delta. So this projects to delta. Let me note the projection by pi. Then there exists a smooth subvariety SH in, and the completion I take near the point omega times 0. So there's this guy, such that if I just restrict to the fiber over 0, then this gives me my original S. And a deformation. So again, I need to consider deformations of the structure sheaf, which are not one parameter, but multi-parameter now. So something like OH tilde over SH. I mean, this SH, I write it down geometrically here, but equivalently algebraically, just some algebra of functions on several variables, formal power series. So there's an algebra over this algebra functions on SH, such that if you reduce it, model all the generators, you get your original one. So there is a thing like that, which is a universal quantization in the following sense, such that quantizations of X are in one-to-one correspondence with sections of this projection pi. And this means that every quantization so that is every quantization OH is obtained from this universal one by restriction with respect to this section. So the picture is as follows. Kind of our basic deformation space has some parameters which are purely commutative. And then there is one parameter which gives quantizations. So there is a universal deformation of the structure sheaf over something like this. If you just look at the part which goes along here, then this is a purely commutative deformation. So no non-commutativity happens here. So these are symplectic deformations. And then quantizations you obtain as follows. You consider some curves here which project one-to-one onto the disk. So some sections of the projection. So this is graph of S. And then quantizations correspond to curves like this in the general parameter space. So it's a bit of an ugly formulation, but that's how things are, unfortunately. I mean, that's the best you can do. So if, for example, you want to identify Poisson deformations and quantization, you just know that every curve like that is uniquely defined by its projection to these coordinates, because you know this one. So in the sense, there is a bijection. But it's much better to think of it as being parts of the whole picture defined over this thing which has dimension, the original dimension plus 1. And in the general Poisson situation, the picture is also similar, except that this guy is pretty bad. So the advantage of symplectic case is that this guy is pretty good. And so it's also smooth, so its dimension is automatically dimension of this guy plus dimension of S. And so you can completely see how it goes. By the way, there is an open problem in this business, which I think is, well, maybe not so very interesting, but I sort of know how to, I have a plan of how to solve it, but nobody bothered to do this. So the interesting question is to see how exactly this thing sits in this space. So it's perfectly well defined. There's some kind of curved embedding of the smooth variety into the RAM. And also here, it's something curved. And we know that if X is compact, then by Bogomolov theorem, this thing here is actually a quadric. So it's given by one quadric equation. And in general, I think there should be some kind of answer which would involve something like Rosansky-Witten classes of your symplectic varieties. But I don't think, so I more or less know how to compute the answer, but I didn't do it. So if somebody wants to do a nice calculation which has some meaning to it, then you're welcome to try. I hope it is a quadric also, but I'm not really totally sure. Okay, so these are the statements of both theorems. I think now is a good time to make a break. And after the break, I'll try to explain the basic ideas which go into the proof. Now, these are the statements. Let me try to give some idea of how the proof goes. So I start with the symplectic story. Oh, I forgot to say. So this, the reference for this are like this. And for the quantization business, so the algebraic part was done by me jointly with Roma Bezrukavnikov. Also, I think it's published in 2004 or something. But actually, holomorphic case was considered before. So this is algebraic. And then a holomorphic case was done by Tsigan and Nest. I forgot when, but before. Holomorphic case. And they were really based on Fedosov. So I think the paper by Tsigan and Nest, which Enrique mentioned, is also this one. Yeah. So they are closer to Fedosov's original constructions, were further apart, but nevertheless it goes back to that one, and I will explain this when the time comes. But let me start with the just symplectic deformations, so Poisson deformations. So first, symplectic deformations. Let me start with the holomorphic situation. Case, which is the simplest to understand. So here, locally, you have Darboux theorem, so locally there's nothing to prove. Locally, there are no deformations. Darboux. But then, of course, there are isomorphisms between deformations. And what are those isomorphisms? So we have a Lie algebra of Hamiltonian vector fields. So these are vector fields which preserve the symplectic form. But you can show it's not difficult. It's a kind of basic effect of symplectic geometry that all Hamiltonian vector fields are of the form. So what's a vector field? It's basically a derivation of the ring of functions. So for every function on symplectic manifold, you have a derivation which is given just by Poisson bracket. As again, Enrique explained. You can show that everything which preserves the form is locally like this. So this is, of course, closed under the bracket, because if you have two things which preserve the form, then so does the commutator. And so just by general nonsense, deformations of X are classified by H1 of X coefficients in Hamiltonian vector fields. Just as if you just consider usual deformation theory, then you say that locally there are no deformations. But when you have local trivialization of the deformation, then you have to patch them together. And this is classified by vector fields, so the whole thing gives you a cycle in H1 of vector coefficients vector fields. Here it's the same, but with Hamiltonian vector fields. Now, if you look at this, you might think that Hamiltonian vector fields is the same as functions. This is almost true, but not quite, because if you put a constant function here, then the vector field would be 0. So, in fact, what you have is a short exact sequence, so there's constants, just a constant sheaf. Then there are functions, and there is a Hamiltonian vector field. Because conversely, if you have something for which this HF is 0, then it's easy to show that this thing must be closed. So it's a function which is closed, so it's constant. And if you have this, there is a long exact sequence of cohomology associated to this. In particular, we have a map from H1 of X coefficients in the Hamiltonian guy. It goes to H2 of X with coefficients just in C. And then it goes to H2 of X with coefficients in functions. And on the left, you have H1 of coefficients in functions. And H1 of X with coefficients in C. But my basic assumption on the manifold was that this is surjective. So this means that this map is 0, and this map is also surjective. So first of all, this is a subset here. This is just second cohomology. And in fact, this is identified to what I denoted by H2F of X. So this shows that, at least at first order, deformations are parameterized by this guy. Then you need to work a little bit to show that there are no obstructions, so that everything is smooth, but basically that's the idea. This is the homomorphic case, so this is like 1A. So how do we do the same algebraically? So algebraically, it's slightly more difficult because we no longer have the Darboux theorem. Because by algebraically, I mean that I want sheaves in Zariski topology, which means that my open subsets are just complement to algebraic subvarieties. So they are rather large. There is no such thing as a small neighborhood. And so we have no local Darboux. So we have a formal Darboux, and this can, if you look at the formal neighborhood of the point, then you have a Darboux theorem. This can also be used, but for now, let's stick to. So we have some, say, affine open subset, but it can have non-trivial symplectic deformations. However, we know that as an algebraic manifold, an affine thing has no deformations. So all the non-triviality here concerns the symplectic form. You basically have the same U, but you change the symplectic form. So let's consider slightly more than just trying to classify deformations. Let's consider the groupoid of deformations. So we have some deformations, and we have isomorphism between them. And you can show that the groupoid of deformations of U is the following. So we have closed two forms, and we mod out by, well, vector fields, but those using the symplectic form, those you can identify with omega 1. And the action is very simple. You take a one form and you add, so omega goes to omega plus df. So these just have to be closed. There is no condition because you have something which is non-degenerate, and then you add a small deformation. So non-degenerate, it stays non-degenerate because kind of the leading term is non-degenerate, but it has to be closed. So it's closed to forms. In fact, you can even write it down nicer, so you have something like a complex. Starts with 0. So it's a certain truncation of the RAM complex. So it's like the RAM complex, but without the first term. So we start with 0, then there is omega 1, then there is omega 2, omega 3, and so on. And so your deformations are given by elements here which are in the kernel of the differential. And isomorphisms between deformations are given by classes here. And so the whole thing is the quotient of this by this. This is local. But then by completely general nonsense, which I don't want to go into this, but it's really standard in the deformation theory. So by general nonsense, so these are sheaves on the manifold. So it turns out that exactly the same statement true holds globally. Globally, deformations are classified, correspond to. So you take, so let me denote this by F1 omega dot x. F stands for what they call stupid filtration in the sense of dealing, but doesn't matter. So deformations correspond to cohomology classes in second hypercohomology group with coefficients in this guy. And then there are isomorphisms, and isomorphisms correspond to H1. And if you just say compute those things by check cohomology, then it's very easy to see. So you have deformation. So locally you have some classes here which are closed. But then locally in the Zariski topology, so for fine guys. But then on intersections, they match together. So there is an isomorphism between them, which is given by elements here. And then the whole thing gives you a cocycle in the check complex which computes this. So that's how it works. And so this F1 omega is an algebraic replacement for Hamiltonian vector fields. Because you can do the same thing holomorphically. But then holomorphically, this complex is actually locally exact except for the first term. And here the kernel is exactly Hamiltonian vector fields. So holomorphically, this is the same as cohomology X of X coefficients in Hamiltonian vector fields. And algebraically, this is what gives out deformations. And we again have exactly the same exact sequence. So we have H, this H which I need, goes to cohomology of X coefficients in the full drum complex, which is just drum cohomology. So this guy sits inside the full drum complex, and the quotient is just functions. So this goes to H2 of X O X. And again, this map is surjective. The map here is also surjective, so this turns out to be my H2F of X. So basically, the same strategy works in the algebraic setting. You have to phrase it a little bit differently. And this is the end of the proof. So this is the main idea of the proof. Now let me do the same thing for quantization. So for quantizations, this approach doesn't really work, because even if you start with things which are affine, you don't have the Darboux theorem, and much less you have a classification of quantizations on affine guys, so it doesn't help you to consider affine things. You really need to go to a formal neighborhood. So we need some kind of technology to deduce global facts of, about algebraic varieties from the behavior in a formal neighborhoods of points. So for quantizations, so two quantizations. Unfortunately, such technology exists, and it is known as, by the name of formal geometry. And it was introduced originally, I think, by Gelfand and Kashdan. A long time ago, like 71, I guess. So, and the basic setup is the following. So we have some X, which is smooth, algebraic variety, dimension D. So we know that since it's smooth, then for every X, we have a formal coordinate system in the neighborhood of points. So we fix a formal disk. So we take A, just the ring of formal power series in D variables. And for every X, we have an abstract isomorphism between, so we take the ring of formal germs of functions on X near X. And this is abstractly isomorphic to A. The isomorphism is not canonical, of course. So what we do, we consider the space of all such isomorphisms. And we call it the torsor of formal coordinate systems on X. So the torsor of formal coordinate systems. So formally, it's the space of pairs of X, and then isomorphism between the formal completion and A. And then an observation is that this is not such a bad thing as you might think. So it's an algebraic, it's a scheme in the sense of Grothendieck. So it's an algebraic variety, which is unfortunately infinite dimensional, but it's not so bad. So it's a projective limit of some perfectly well-defined finite dimensional algebraic variety. So the first kind of step in this tower, so when you have an identification like this, it induces identification to after you truncate by certain order. So like in order 1, you just get an isomorphism of tangent spaces. So if you truncate it by order 1, then you just get the principal bundle of frames on X, which is a perfectly well-defined algebraic thing. Then you add higher order terms, so you get some more bundles. But nevertheless, it will be a principal bundle with respect to a certain group. So what is the group? Well, every two such isomorphisms differ by an automorphism of A. So we have a group of automorphisms of A, and this is again pro-algebraic group. So it's actually projective limit. So we have, when you have an automorphism of this formal neighborhood, then on first order it just gives an automorphism of a tangent vector space. So it goes to GL of the tangent bundle. And then there is some kernel, which is unipotent, pro-unipotent. And then this guy over X is a completely canonical torsor with respect to this group out of A. But in fact, there is slightly more. So this algebraic group, it actually has a Lie algebra. So the Lie algebra out of A, as you can expect, the Lie algebra of automorphisms is given by derivations. So these are derivations of our algebra A, but only those derivations which preserve the maximal ideal corresponding to the point X. And you can have actually more. So you can also have derivations which do not preserve the maximal ideal. For example, if you have some non-trivial vector field on X, which is non-trivial on X, then it gives a derivation of this formal neighborhood. So this sits inside the Lie algebra of all derivations. So that is like a short exact sequence of Lie algebras. And the quotient is just the value of the vector field. And in fact, this whole Lie algebra also acts here. derivation of A also acts on this coordinate torsor, which means that there is a map, canonical map, from this Lie algebra to the Lie algebra vector fields on this guy. So what happens is that some of the derivations can be integrated to actual automorphisms, but some cannot. So if you have a vector field which actually is non-trivial at the point, then it defines an infinitesimal automorphism. But since it does not preserve the point, you can't integrate it to any meaningful automorphism. But once it vanishes at a point, you know that you can actually integrate it. So what Gelfand and Kaledin did, they kind of axiomatized the situation. So first of all, well, I forgot what the terminology was, but these days, a setup like this is called the Harish-Chandra pair. Harish-Chandra pair. This is something like an algebraic group, a Lie algebra H, and then an embedding from the Lie algebra G corresponding to G to some kind of bigger Lie algebra H. And then G has to act on H. And the basic idea is the same. It's you have some Lie algebra, and then some subalgebra is integrated to a group, but not the whole thing. And then there is a notion of Harish-Chandra torsor, which is basically something like what you have here. So you have your X, then you have a principal bundle with respect to the group. So you have an action of the principal bundle on the total space, of the group on the total space of the principal bundle. And the corresponding Lie algebra acts horizontally. And then this action is extended to the action of the Lie algebra H, which is no longer horizontal, but maybe projects to X. And there are all sorts of theorems about Harish-Chandra torsors, which kind of expand, generalize the well-known theorems about principal bundles. So this is the basic setup. Now, what has it got to do with quantizations? It turned out that we can describe quantizations in a similar way, except that the group and the Lie algebra will be different. So now we have X and we have a quantization. And then we know that if we take some point in X, so a point defines a maximal ideal in the structure sheaf, and this extends to a two-sided ideal here, so we can take a completion of this guy here. And we know that abstractly, this must be isomorphic to the Weyl algebra. So what we can do, we can consider the space of all such isomorphisms. It's a space of pairs of X and an isomorphism like this. And again, you can show that this is a pro-algebraic variety which projects to X. Well, projection is clear, you just forget the isomorphism, but it actually goes to the coordinate system torsor, because when you have an isomorphism like this, you can mod out by H, and then this gives you a formal coordinate system on X. So what is the group here? The group, as you might expect, is so the group is the group of automorphisms, well, H-linear automorphisms of the Weyl algebra D. And again, it has a Lie algebra, which is the Lie algebra of derivations here, which preserves the maximal ideal, and it extends to a bigger Lie algebra of all derivations. So this is a Harish-Chandra pair. And M is a Harish-Chandra torsor with respect to this pair. So here we have out of A, And here we have out of D. And I don't write Lie algebra, but they're in the picture. I write Lie algebras, but they're in the picture. And then, again, just since you know that such an isomorphism always exists locally, you can prove that there is a one-to-one correspondence between quantizations and those torsors. Then we have a correspondence between quantizations and torsors with respect to this guy. So it seems you gained nothing. You had one abstract thing and you traded for another abstract thing. But for this, we can now apply some kind of familiar machinery. So I probably don't want to give you the proof of the theorem because it's not very instructive. But let me explain how you get the canonical parameterization of quantizations. So one interesting thing about the theorem was that we actually have the space parameterizing quantizations canonically embedded into the Ramka homology. So how does this come about? For this, I need to explain a little bit how this looks like and how this looks like. So what is the algebra of derivations of D? In fact, maybe I should write it here. And observation number one is that if you have some derivation of the Weyl algebra D, then every derivation is inner. There exists an A in D such that this delta is 1 over H commutator of AB minus BA. So the Weyl algebra is very rigid. All the derivations, well, I mean, you have to divide by H, because since model H, the algebra is commutative, every inner derivation goes into the kernel. I mean, it's divisible by H. But other than that, all of them are on this form. So this you have to prove, but it's not difficult to prove. So we have a map from basically D itself, with a bracket given by commutator to the derivations. This has a kernel, because if you have a constant, I mean, in general, if you have an element in such some algebra which is central, then the corresponding inner derivation is 0. But this D has a very small center, but it does have a center. So the center of D is just the algebra of constants. And so this has a kernel, which is just an abelian Lie algebra. And we have a short exact sequence like this. And you can show that this actually also occurs on the level of groups. So this is actually an extension of central extension of Harris-Chandra pairs. So here we have some like D star. This is out D. D star means invertible elements. Well, I mean, and here we have some kind of unipotent kernel, which corresponds to this guy. Well, it's not quite D star, it's something a little bit modified. Now, so our quantization gives us a torsor with respect to this guy. And we can ask the following question. Can it be lifted to a quantization with respect to this guy? If you just have usual principal bundles, then it's a well-known situation. So we have some central extension of groups, and you have some variety X, then there is a canonical map from the set of, so non-abelian cohomology of X with coefficients in G, which is just a set of isomorphism classes of principal G monads, goes to, so this is abelian, goes to the second cohomology of X with coefficients in the, so it's abelian, so it gives actually a sheaf on X. So this is a vector bundle associated to this principle, to this group. And you, for example, encounter a situation like this when in the story about Zumaya algebra. So you have some kind of algebra on your X, which is locally a matrix algebra, but globally maybe it's not a matrix algebra. Then this corresponds to the fact that you have some kind of PGL torsor, which you want to leave to GLN torsor. And then the kernel here is C star. So you get a certain class in H2 of X with coefficients in the sheaf of inversible functions. And there are many other situations when this pattern occurs. And it's not difficult to construct either. You can, for example, do it locally. Then you try to patch things together and you get a cocycle. Now, the point is, and this has to be proved, but it's quite straightforward, is that in this Harish-Chandra torsor story, you get exactly the same phenomenon, but now the cohomology has to be the Ram cohomology. So this thing acquires a canonical connection, and this has to be the Ram cohomology. So for HT torsors, you get a map. So in our case, and this is the extension which I have in mind, so in our case, this is a map from quantizations of X to H2 the Ram of X with coefficients in, so here the kernel is basically just constants except that you have this parameter H. So this will be, if it were just something like this. Just cohomology of X, I mean, let me stick to C with these coefficients. And this is the same as just the Ram cohomology of X, but then you take formal power series of coefficients of the Ram cohomology, which start with term H to the power -1, then 0, term H, H squared, and so on. Okay, so this is my parameterization. So what happens is that there is always an abstraction in this term, 1 over H. And you can show it's not difficult. This abstraction is exactly the class of my form omega. So there's always an abstraction. But then depending on quantization, you also might get some higher level abstractions. Or maybe there are no abstractions. Depends on quantization. But just considering this map gives you, first of all, a map which is injective. And then it completely parameterizes quantizations. So this map parameterizes quantizations. By the way, I totally forgot to say this, but in the symplectic deformation picture, you can also write down a map which parameterizes deformations quite canonical. There you can do it right away. There, the map is as follows. If you have a deformation of your X plus some symplectic form, then just by general deformation theory, the Ram cohomology of your guy stayed constant. So it's canonically trivialized under deformation. And what changes is the class of the symplectic form. So there you have a period map from deformations of X omega to the Ram cohomology, which just sends a deformation to the class of the symplectic form. And then the theorem is that this is enough. The theorem is that once you know the class of the symplectic form, you know the whole deformation, everything parameterizes this. So this is some kind of non-commutative version of that guy, which is given by this kind of strange abstract nonsense, but nevertheless turns out to work. And so if you want an actual proof, then it works more or less similarly. But so you do it step by step on H. So, I mean, this is the map, and then the theorem is that if you have any class here, modulo some conditions, I mean, class which corresponds to this SH, then it can be realized by quantization in a unique way. So you need to construct this torsor, and then you do it by considering a filtration here by the powers of H, and at every step, you get a short exact sequence like derivations of D model h to the power n, and then model h to the power n plus 1. And here the kernel is just, again, abelian. And this is just, in fact, you can check that this is, so all derivations are inner. So for D, it would be just A. Here it's A modular constants. So again, we have a picture of the similar form. So we have the abstraction map, and you can analyze this and get your result. So using this, we prove the result. Right, so this is kind of the main idea of the proof. And if you want, you can also rephrase the symplectic statement in a similar fashion. So you can consider Poisson deformations of A. So Poisson deformations of A are also all trivial, also isomorphic to A of H. And you can play the same game. So you can consider a torsor with respect to now the group of symplectic automorphism of this way. And then you get the step-by-step construction, and then you prove your result. Although what I presented here is kind of an earlier version, which is, I think, simple. So one interesting point here. I briefly mentioned before the break that you get some kind of Rosansky-Witten classes in the picture. So how do they come about? Turns out that when you have this extension, so it's a Lie algebra extension of this guy by this guy, and you can ask how trivial or non-trivial the extension is. And then turns out that the very first extension is actually trivial. It can be split. And you can see it in geometry immediately, because if you want to write down canonical quantization or canonical star product, then up to h squared you can do it. You can just write f star g is equal to fg plus h times the bracket. So, as Enrique mentioned, I mean, whatever you write, the skew symmetrization of the first term would be the bracket. Turns out that if you do this canonical Weyl product or Weyl product, it is sometimes called, the first term is actually with the bracket on the nose without skew symmetrization. But then already in a square you have something non-trivial. But if you only care about the first two terms, then there is a canonical expression, and the explanation for this is that this Lie algebra extension for n equal to 1 is split. But for n equal to 2 already, it is not split. And then you can cook out some kind of characteristic class of your symplectic variety out of that. And this turns out to be what is known as Rosansky-Witten characteristic class corresponding to the theta graph. Well, anyway, it's an aside. Okay. And now, in the last sort of 15 minutes, I want to mention some generalization to characteristic P, which I don't expect. I mean, let me just mention it because this is something which, first of all, only is available in this context, so it cannot be at present achieved in the general deformation quantization context. And then it has some application. And another thing I should explain probably is what this has to do with the original Fedosov construction. So for Fedosov construction, it's easy to explain. So basically, we parameterize our quantizations by certain torsors plus this Harris-Chandra structure, which amounts to having some kind of flat connection on the torsor in some sense, on the torsor. And those torsors are non-trivial at all stages. But if your X is, for example, affine or something which has no coherent cohomology, and this, of course, is a situation in the C-infinity world. So in the C-infinity world, we don't have cohomology of vector bundles. All trivial. then this huge torsor can be canonically reduced to the very first non-trivial part here, which is the group SP, or the tangent space. So this is a big group, but it has some kind of quotient map to the symplectic group, and the kernel is unipotent. So when you're in a setting where you don't have coherent cohomology, you can throw away all the unipotent parts. So then what remains is a principal bundle with respect to SP, which you know right away. This is the frame bundle of your symplectic manifold. And the only piece of data which you need is this Harris-Chandra structure, which I mentioned, which boils down to basically a flat connection of some sort. And this is what Fedosov did. And then in the algebraic setting, unfortunately, you cannot trivialize this higher torsors, so they actually can be non-trivial. And you have to consider the whole group. But on the other hand, kind of the picture becomes more transparent, so you don't really need to, there is no ansatz you have. So the Fedosov construction is kind of a lucky guess. So you kind of guess that, yeah. Yeah. So okay, I explained about the Fedosov connection. Now let me explain about what happens to characteristic P very briefly, because it's kind of funny. So what happens in characteristic P? It turns out that you can at least start the same story. So you can define quantization exactly the same way. Of quantizations is the same. Just one parameter deformation of our guy given us Poisson structure. And second, the basic example is also the same. Basic example is also the same. So we take, just absolutely do the same thing. We take the Weyl algebra, which is generated by P's and Q's, and H, model the same Heisenberg commutation relations. But first difference you see is the following. So as I said in characteristic 0, this algebra was almost like a simple algebra. So it had a very small center. The only central elements were constants. And all the derivations were inner derivations. So it was almost like a free algebra. And in characteristic P, you suddenly see that this thing actually has a huge center. Has a huge center. Namely, if you take some pi, okay, now there's a clash of notation. Okay, let me rename them x and y, right? So you have some xi, and just raise it to the pth power, then this is central. And also same for yj, are central. Because you can write down, so for example, this Weyl algebra has a natural representation by differential operators in x's, right? So if xi goes to psi of f, the multiplication, and then yi goes to derivation, and you take xi to the power p. Of course, it commutes with x's. The question is whether it commutes with y's. But now the commutator is given by d over d, sorry, xi of xi to the power p. And when you do this, you get p times xi to the power p minus 1, and this is 0 because p is 0. So this thing commutes with x's and y's, so it's central, and similar for y. So this algebra has a huge center. And if you think a little bit, you can see that the center, so this D is a certain quantization of the algebra which are denoted by H. And then the center of D is naturally identified with the algebra of pth powers of functions in A. So there is a Frobenius map which gives an abstract isomorphism between A and A to the power P. So the center is actually as large as the algebra A itself. Big thing. And then you can look at D over the center. Well, D itself is something, but if we invert H, and now I need a formal power series here, so this can be done with formal power series. So the center is so large that this is actually finite dimensional over the center, so it's a modular finite rank. And in fact, it's actually isomorphic to a matrix algebra of the size p to the power n. So maybe I should rewrite this. So D with H inverted is isomorphic to algebra of matrices of size to the power n over the center of its center. And the proof is easy. So again, you consider this presentation by differential operators. Now it is no longer an exact representation because we have a huge center and all those go to 0. But if you consider it as a representation over the center, then it's fine. It turns out to be exact. And I mean, exact in the sense that the map from D to the differential operators is injective. But then it turns out that it's also surjective, meaning that so if you have A considered as an algebra over AP, then every AP linear map from A to itself is a differential operator. Maybe of some high order. And this is what gives you an isomorphism, basically. And so now you want to study quantizations of algebraic variety. You see that locally you have this phenomenon, and also locally there are non-trivial deformations also. There's only one of them. And a meaningful question is to ask for deformations such that this fact of this algebra having a large center is preserved. So we now have some x, which is symplectic, over a field of characteristic P. Then one question one can ask is find a quantization, which I call Frobenius constant. And this means that quantization, which means that this OH is not only an algebra over K of H, but it's also an algebra over the pth power. So it's an algebra over OH or OX, well, the subalgebra of P powers like here. And then you have formal power series in H. And so what we did with Bezrukovnikov, we proved that at least if you assume that X has no coherent cohomology, then such things actually do exist. You can construct them. And they are numbered more or less by elements of the Picard group of X. So you do have those quantizations. So the theorem is more precise, but roughly speaking, that says that if hi of x or x is equal to 0 for I1, 2, 3, then Rabinius constant quantizations exist. But same as here, if you have such a guy and invert H, then it becomes basically at least locally a matrix algebra, and you can arrange things so it's globally a matrix algebra. So then, so moreover, OH with H inverted is a matrix algebra over this P powers, which means the following. So this means that Laurent power series, I suppose, on this guy. So this thing is an endomorphism algebra of some vector bundle E, where E is a vector bundle. Well, we have this formal parameter here, so it's something like X cross this formal disk minus the zero section. So you start with a symplectic variety in characteristic P, and then for nothing, like just out of the abstract nonsense, you get a certain vector bundle. Even if you start with something characteristic 0, you can reduce it to characteristic P, obtain this vector bundle, and lift it back to characteristic 0. And one of the properties of this guy is the following. So we know that, so here we require that there is no cohomology here, but if for some reason all the homology groups vanish, then this is obtained by deformation from OX. This means that this also has no cohomology. So this bundle is such that it has no X to itself in, in degree higher than 0. And so there's a very strange construction, which even in characteristic P, but also in characteristic 0 by reduction to characteristic P, produces you a bundle which has no X to itself. And it turns out that such things are actually quite rare. Like, quite usually in algebraic variety, you would not have anything like this, which is non-trivial. And they can be used, for example, in the study of symplectic singularities, to obtain rather strong structural results. For example, this fact that the whole cohomology of the variety is generated by algebraic cycles eventually boils down to using this bundle E to characterize cycles on the variety. So this is a very strange story. And people, when I give these talks, people always ask me, okay, now let's get rid of characteristic P. And it seems you cannot. And it's a shame. For example, you can do it, so if you do it in characteristic 0 by reduction to characteristic P, you can choose different P. And basically every prime which is big enough would work and would give you a certain bundle E. And the feeling is that those bundles are not quite the same, but they are sums of the same bundles with some multiplicity which depend on P. But there is absolutely no way to prove it. I have absolutely no idea how to approach this. And Also, there is some kind of, I mean, this has not been finished, but there is some kind of way to construct Illustrix quantum groups at roots of unity using similar procedure, at least when roots of unity are like of prime order. And again, there is no way to relate things for different p's, although we know that the answers fit together, but there is no way to see it in the picture. And in the end, you get completely geometric corollaries for X itself. So there is this story which is weird, but nevertheless works. And I don't know whether anything at all has been done about quantization of Poisson manifolds in a characteristic P. Maybe nothing, but I think this is a very interesting area with kind of big future. Okay, I think enough. Yeah.